Okay, YouTube, in our last video, we looked at the slope of a line for a data set here as being some rate of change, okay? And so that's really easy to determine the rate of change, just find the slope and assign proper units. But when we're talking about a data set, and so I give one here as an example of maybe the height of a child, a male child, over the course of, say, 20 years here and how it changes. When it's not a linear data set, I mean, it's approximately linear, it's kind of going up at some slope here. But when it's not perfectly linear, then all we can do is, instead of coming up with an absolute rate of change, is come up with what we refer to as the average rate of change for a given time interval. So maybe the average rate of change between when he was 10 years old and when he was 15 years old, or perhaps between when he was 13 years old and when he's 18 years old, okay? So when we talk about the average rate of change between any 2 points, we're talking about the slope of the line that contains those 2 points. So of course, we know that the rate of change is the slope of the line. But when we talk about the average rate of change between 2 points when it's not necessarily linear, we're going to say the slope of that line that at least connects those 2 points. And this line is called a secant line. So if you've ever taken geometry, we often refer to a secant line as a line that would say, on a circle at least, intersect this twice, okay, pass through it twice. And so given this nonlinear data set here, you can see that we would refer to this as a secant line because if we connect the dots on all that data, you can kind of see how it does the same thing. It passes through 2 distinct points on that given curve, okay? So the slope of this secant line is what we're going to refer to as the average rate of change. And so as an example here, we say that this particular person's height in inches is a function of his age in years. We could find the average rate of change between when he was 13 years old and when he was 18 years old, like how fast this individual is actually growing. And so the way we'll do this is just find the slope of the line containing those 2 points. And so our slope here, the average rate of change of this gentleman, would have been y2 minus y1. So we'd have a height of 76 inches minus a height of 57 inches, change in y. And then we say our change in x would be between the years of 18 years old and 13 years old. So I'm actually going to subtract these here, and I would get 19 on top, and I would get 18 minus 13 on bottom is 5. So I want to make sure we label this, as a matter of fact. We're going to label the top here with inches and the bottom here with years. And so when we find actually the slope of this, we're going to get our calculators out here, and we'll actually get a decimal value for this, maybe out to 2 places here if we need to go 2 places, which we won't, I don't think, here. So 19 divided by 5, 3.8. So we could say that the slope, or the average rate of change between ages 13 and 18 would be this. We say 3.8, and we're going to label this in inches per 1 year. Okay, so inches per year. And you know what? You can see that that would be the slope of this line between 13 and 18, where there was a great difference between those two values. If we were to look at between the ages of 5 and, say, 10, you might not observe as steep a slope. It'd be a little bit flatter, looks like here. And even between, say, 3 and 4, okay? The points at which you're comparing makes a difference in the average that you're trying to find, essentially. So what we're going to do is formally define the average rate of change of a function. We're going to say let x1, f of x1, in other words, some x1, y1, and x2, f of x2 be distinct points on the graph of a function. Then we say that the average rate of change of f from x1 to x2, at least between those two given data values, is always this right here. And what I want you to see is this is really the slope average. Okay, this is the slope formula. So we have y2 minus y1 over x2 minus x1. It's just that we're always going to be given two x values that we want to find the average rate of change between. And so f of x2 and f of x1 really just represent the y values at those points. But you can see on our graphic here, if we had some blue graph and I said, what's the average rate of change between here and here? Well, on average, it increased about that far over that far. It'd be the rise over the run ratio, or the slope of the secant line passing through those 2 points. So what we're going to do here is this. We're going to find the average rate of change of f of x equals x cubed from these distinct x values here. So looking at this first one, we'll take a look at it. We say between x1 equals 0 and x2 equal 1. So what I want everybody to realize is this. We're really saying I want to find the average rate of change of a line that's passing through these 2 points right here. x1 is 0, and then we'd say f of 0 would be the y value there. And then we'd say that the second point here has an x value of 1, and then we'd say then this must be f of 1 right there. So this is our xy pairs right here. The only thing is that we don't actually know what f0 and f1 actually come out to equal yet. So we do know the function here, and the function here is x cubed. So if I were to plug 0 in direct substitution wise, we would say we would get 0 for an output. So really this first point right here, what we're going to do is we're going to say this is really the point 0, 0. And then we say the second point, which is 1 comma something. We need to find out what 1 cubed is. Well, we don't have to take very long on this one. We say 1 cubed. It's actually just 1. So we say the point 1, 1. So we would say between these 2 points on the graph, if we wanted to find the average rate of change of our graph between those 2 points, we would say it's y2, which is our 1 here, minus y1, which is 0. And we get the same thing with our x's. We say x2 is 1, x1 is 0. So it looks like we get a slope of 1 over 1, or an average rate of change of 1. And so this is our average rate of change, and specifically between these two x values on the graph. So what I've done here is I've actually put this into GeoGebra, and you can see that this is actually our x cubed curve right here, and I already have these 2 points in. So we say between x equals 0 and 1, what was the average rate of change? Well, I say, well, it'd be between the slope between the 2 points on this graph at 0 and 1, or the secant line between 0f of 0 and 1f of 1. So you can see that the slope of this red line here is clearly 1. Okay. When we look at this next example, what I want to do is actually want to start with the graph of it. We say between x equals 1 and x equals 2. So the way this is going to be different is we're going to say, well, what I'm going to need to do is I'm going to need to slide this point out here to 2, 8 is what we get here. 2, 8. Or in other words, 2f of 2. And then here we're going to get 1f of 1. We will say, what's the average rate of change of our graph between these 2 points right here? So I can say, well, it's increasing greatly, but the average rate of change would be the rise over run of the secant line, which is up 1, 2, 3, 4, 5, 6, 7, and over 1. So a slope of 7, or an average increase rate of 7. So what we're going to do is we're going to take our algebraic approach now. We're going to put this to use. We're going to say between 1 f of 1 and 2 f of 2. So the only thing we need to do now is go find f of 1. And from our last example, we know f of 1 is 1. And then f of 2, which is just 2 cubed, when we plug that into our function here, we get 8. So we would say that our points that we're finding the slope of the secant line through are really 1, 1 and 2, 8. And so finding the slope of this is actually just pretty elementary. We'd say 8 minus 1 is our change in y, and our change in x is 2 minus 1. And what we end up with is 7 over 1. Or in other words, 7 units per whatever unit of x of run here would be our average rate of change. So for our last example here, we say between -2 and 0 on our graph. So I can go back over to our graph, and again, how about we start with it? Slide this back in a little bit here. So we'll go to an x value of, oops, sorry. Try this again. There we go. We'll go to an x value of -2. And the height of our graph at -2, it looks like, is -8 here. And then we'll go to 0, which is at 0, 0. So again, we could use the graph here just to count. We could say, well, it looks like it's going, I guess, up 8 and over 2. Up 8 over 2 would be up 4 over 1 would be 4. The same thing we're about to find algebraically, essentially. So let's go ahead and suggest this. We say between -2 and f of -2, between that point and 0 is our next x value, and f of 0 there. So really quickly here, we know that f of 0 from our first letter over here, f of 0 is equal to 0 here. F of -2, now we are going to find this here. We're going to say this would be a -2 cubed, which is a -8. But now that we have that, we can say really the slope of the line through the 2 points would be passing, actually, the line would be passing through these 2 points, -2, -8, and 0, 0. We need to find the slope of the line passing through those 2 points, that secant line. So we would say maybe 0 minus a -8 and 0 minus a -2. Make these positives, but we're going to get 8 over 2. And that 8 over 2 reduces, and we would say that the average rate of change of the graph through those 2 points is an average rate of change of 4. Cheers.